Hey out there, everybody. Good morning.
Hello,
Uh,
everybody.
it's a Thursday once again. Please, as you join us in the chat, wherever you are watching us, we're live on YouTube, Twitch, Twitter, LinkedIn Live, Zoom. Go ahead and say hi. Let us know where you are coming from. We love to see the OpenCV community checking in from around the globe. Hello,
So
London,
please,
Ontario.
everybody, make sure that you select everyone from that drop-down list so that everybody gets. I'm seeing some messages. They are from. Yeah. Okay.
Hmm.
Thank you. Thank you. Select everyone so that everybody gets to know where you're from. That's excellent. Thank you.
Yes. Good morning out there, everybody around the world. I think we are now live on all of our various channels. Yeah, it looks like we're up on Twitch, we're on LinkedIn, etc., etc., etc.
All right.
I'm pretty sure. Let's make sure
That's
LinkedIn is
Escondido.
behaving.
That's very close to my house.
Is there people
Germany,
from India
Baja
as well?
California, Escondido,
Yeah, people
Italy,
from all over
Dallas.
the world, including India. We have a bunch of people from India. I'm pretty
Yeah,
certain a few
Wow,
from
nice.
Bangalore as well.
indeed.
Oh, great, great. Before the meeting, I tweeted out about this
I
whole thing.
saw. I just reposted it.
Thanks.
That's
Yeah.
awesome.
I'm double checking our. Okay. Yeah, looks like we're live everywhere. All right, cool. Yeah, everybody, tell us where you're coming from. I'm seeing some folks popping in over on YouTube, Germany, France. Here in Zoom, we've got Savannah, Georgia, Bhopal, Bangalore over on YouTube. Love to see it. Love to see it. This is going to be a fun one.
This
I
is
feel
going
like the
to be fun.
last, I feel like the last couple episodes of this show have been, I've learned a bunch of stuff. At a certain point, I'm worried my mind may explode, but we'll see what happens. Howdy, Ann Arbor, Chennai, Nigeria. I think we can go ahead and get started, Doc.
All right. Hello, everybody. Welcome to OpenCV Live. Today, we have a very special episode for you about NeRFs, neural radiance fields. And joining us for this episode is Soumyadip Sarkar, who is from OpenCV University. He's a computer vision engineer at OpenCV University, and he has prepared the presentation. We'll go over it together. And it's going to be very, very interesting because neural radiance field, they represent a very big jump, technological jump, as far as 3D reconstruction, etc., is concerned. And then there will be a follow-up episode that we will go over about Gaussian splats. So, but for this episode, we wanted to cover NeRF so that you get a history of how this kind of technique emerged. All right. So, Soumyadev will introduce himself in just a bit, but before we do that, we have Phil Nelson with us, who is the Director of Content and Creative at OpenCV. Phil produces the show, and if anything goes wrong, it is his fault.
Yes, that's right. It is me. It's PHI LLIP, your co-host with the co-most, the second banana who is second to none. I'm also your plus one and only, and you out there know it's Mr. Nelson if you're nasty, but you can call me Phil. I'm here to remind you of a few things we do on every single episode of OpenCV Live, the first of which is a giveaway to you in the audience. A little bit later in the episode, I will be asking a trivia question based on the presentation here today, and the person that answers that trivia question correctly in the Zoom chat will win the OpenCV University course of their choosing. You can go to opencv.org/university to see what courses are on offer. We're also taking questions from you in the audience, so feel free to ask those questions whenever you want, wherever you want, wherever you're watching. We're live on YouTube, Twitch, Twitter, LinkedIn, and Zoom. In Zoom, please use the Zoom Q&A button at the bottom of your screen. But if you're on YouTube or elsewhere, just use the chat, post it in there, and I'll do my best to bring it up as conversation permits. Did you guys know that OpenCV is a nonprofit organization that releases open source software? It's true. Satya, would you like to tell the folks a little bit about why it's important to support OpenCV and some of the ways that they can?
God, we take the phrase of nonprofit really
You're
seriously.
telling me. You're telling me.
So, so OpenCV, it takes a lot of effort and time and engineering resources to bring this library to life, and also bring all the material that we do for free to life. So, if you are if you are in a big organization, I would definitely ask you to go and talk to your manager if it is possible for your organization to become a silver member or a gold member. And if individually also you can contribute, as you can see here, you can do individual contributions through Stripe, through PayPal. You can also go to our GitHub page, and if you're set up on GitHub, that's also possible, right? We have a bunch of people on GitHub supporting us.
Yeah, shout out to the 11 there on GitHub. We picked up a couple in the last few weeks. Appreciate it,
That's
folks.
awesome. Really appreciate it. And last but not the least, we also have a merch store, which you can visit. And we have many new designs coming through, so you can go and participate there as well.
Yes, indeed. That's right. There's one more bit of business to talk about at the top of the show here, which is the perception challenge for bin picking. You want to gas the people up a little bit about this one some more?
All right. So this challenge is going live on February 1st. You can register even now, right? But the challenge officially goes live on February 1st. There is $60,000 in prize.
I believe we just passed 500 registrations, so keep them coming.
That's awesome. So in this bin picking challenge, the basic idea is that there are these pieces, that industrial pieces that a robot needs to pick up, and all the data has been collected for these pieces, and you need to find the pose of these pieces, how they are located in space. We are also giving a reference implementation. So if you do not know anything about how this thing is done, you can see the reference implementation and try to improve upon it, right? And people who join, we will also start giving out, what are the other techniques other people have tried, so that you get a sense of what could be useful. So amazing prizes. If you are in this field already, this is a great opportunity to shine, because people who qualify, the top the top few people, I think the top two people will get a chance to present at CVPR workshop. And as you know, that CVPR is the biggest conference on computer vision in the world. Very, very prestigious. I don't know, 10,000, 15,000 people show up there. It's a very difficult to get into. But through this, you can get into the CVPR workshop if you participate and win the first two prizes.
Yeah, and these, being able to present at a workshop at CVPR is a huge deal. The 99% of people in the computer vision and AI industry will never get this opportunity. So, don't let it pass you by. Join the bin picking challenge.
Yeah, and a big shout out to our collaborators, the BOP Challenge people, University of Hawaii, and we also have sponsors. Intrinsic is the prime sponsor of this competition, and we also have Orbic as one of our sponsors. So thank you, Intrinsic.
Yep, big shout out to Intrinsic and Orbic for providing so much support and prize money, of course. Go check them out and tell them OpenCV sent you. With that, I think that's about all we got to talk about at the tip top of the show. Let's get started, eh?
All right. So Soumya, why don't you give a brief introduction of yourself, and then we'll share the slides and start the presentation.
Yeah, sure. Howdy, everybody. So I'm Swamedeep. I work here at OpenCV University as a computer vision engineer. So before that, I did my BTech on electrical engineering, and right after that, I joined Triple IT Delhi. But I worked on autonomous vehicle as a research engineer, mostly on perception, and all the OpenCV, all the computer vision that I know is from those experience, and now here I am at OpenCV University. Yeah.
Right.
So
Welcome.
let's start the presentation. Let me know if it is visible properly. And yep.
Looks good.
Yeah. All right. So today, the agenda that we signed up for is that we are going to go through the NeRF, how NeRF works, what are the different details and mathematical caveats that NeRF has, and what the problem it is solving, and how you can use it for like creating 3D representation of a scene, right? So here you can see, like right out of the bat, that there's a, a few years ago there was a commercial recorded for McDonald's only using NeRF. So this is a very advertisement that happened, and few weeks ago or months ago there was an Emmy award that NeRF won. Okay, from for Phoenix Suns, which is the category of like technical advancement in sports promotions, right? There were two Emmy awards on NeRF, right? So quite hot, quite exciting field, I'll say. And if you are in computer vision, please like look out for these technologies, because these are going to be very useful, right? So this is going to be the agenda. So we are main thing that we're going to go is that we are going to understand what this technology, which problems the technology solves, how it solves it, right, and how you can use it for your problem statements, right? So uh, before going in all the like nitty details of NeRF, let's understand what is forward rendering, some basics, forward rendering, inverse rendering, and some things along those lines, right? So forward rendering, which is nothing but say you have the 3D scene, right, and you know the camera pose from where the images were taken. Now you collect a lot of you have a lot of you have a 3D scene, and from there you try to get a 2D render of the scene, which is like forward rendering from 3D to 2D. It's very simple. And one of the example is Cornell box. Like back in the days, folks from Cornell set up this on the left side, uh, uh, the setup where they have put up different lighting settings, walls, and boxes, right? And they know where each and every object is. And after that, what they did is that you took those information, went to their computers, put those boxes, walls, lightings into this proper 3D Cartesian space, and from there they try to get a 2D image from a specific camera angle, right? And you can see it is very, even though it is like 1900, is very old back, you can see that it's very similar looking, right? So this is what forward rendering does. And then comes one of the application of forward rendering, which is like, okay, novel visual synthesis. Novel visual synthesis is something like, okay, you have given the camera position, you know the image, right? Now your question is to the model is that if I move the camera slightly toward the x-axis and rotate it somehow, and what will be the camera, what will be the image from that camera position, right? So it is something like, okay, your model haven't seen those images, you're given those unique poses, you are trying to get the new image, right? So after that it comes the inverse rendering, which is totally opposite, which is you have lots of image of a scene. Now what you want to recover is the camera pose and the 3D scene, right? This is what NeRF is doing, or Gaussian splats is doing, right? So this is the problem statement. So uh, this is also done by 3D reconstruction. 3D reconstruction is like more of like, okay, you take a bunch of images like from different angle, and you generally 3D reconstruction from classical computer vision point of view, it will, what it does is that given those images, it will try to generate a point cloud of the scene, right? So one of the thing is like using cone map for this 3D reconstruction or structure for motion. So you're getting a structure, point cloud structure of the 3D scene given those images. And cone map does exactly that. So how it does is that from a very 1,000 feet overview is that what you get generally is that you get the camera position, which is XYZ coordinate in Cartesian, and also the viewing angle, like in roll pitch yaw. So that is the camera pose, and also you get is that all the points that is describing the scene, which is the point cloud, which is nothing but XYZ points, right? So how they do that generally is that in classical computer vision is that you have multiple images of the scene, and you perform feature matching. So you do feature extraction, you do feature matching, and from there you try to get the essential matrix, and from essential matrix you try to from instructional material, you know how the where the camera is located, and from there you try to do triangulation to get the 3D points. I know it's very abstract, but you can go through one of our blog at Learn OpenCV, which describes it very clearly. But
But
this is the yeah.
let me
Hello.
just summarize it, right? Although Sumit explained many steps. Essentially, what you do is you take pictures of the scene from many different camera locations, right? So you have a collection of scenes. In these scenes, you try to find features, right? Some points which you can actually locate in at least two cameras, right? So in multiple cameras, you're able to locate a feature. And if you have at least two cameras, like just like we have two eyes, right? And by triangulating, you can get the depth estimate of a point, right? And if
Yep.
the same point is seen from multiple cameras, then you can actually do a more sophisticated optimization, right?
Right.
For finding the 3D structure of these points. Now, the reason we don't get a very dense map, we get 3D point cloud, is because not every point is a good feature to track, right? Sometimes if there is a flat surface, you cannot actually track the feature there. So most of these structure from motion algorithms would actually get 3D structure of a point cloud. So it's not like a dense structure. And sometimes you make a mesh out of those point clouds so that you can fill in the gaps. But we also need to know the camera locations, right? Automatically, it actually finds the camera locations. So the best tool that does this work right now is called CoalMap. So if you ever need to find the camera location from just a bunch of images of the same scene, go and check out CoalMap.
Yep. You can download any video from YouTube and just run Gold Map on it. You will get a 3D reconstruction of it. It's that good, to be honest. Yeah. So this is how the structure from motion works in. So remind you that this is the first step of how NeRF works because you need to create the data set of the images and then you do structure from motion. This is the first step. We'll come back to this later on. So now we understand what are like what is 3D reconstruction, what is novel visual synthesis, but like what are the different application of NeRF or 3D reconstruction, right? So this is generally like might have seen the Apple Pro glasses, right? So using those, you can have a 3D like augmented reality of different tabs are open, you're playing games, you can interact with the hands, right? So like generally, so those things are done using 3D, right? There's a 3D reconstruction and trying to map it, project it in front of your glasses. Apart from that, there are like also application on SLAM, on navigation, robotic navigation. There have been a lot of paper on SLAM. This is the one of the uh, figure that I got from a paper from MIT, and then there's a simulation. So generally, what happens is that you create a digital twin of this environment. But now that you can capture a 3D scene of an entire 3D scene, you can use that for your robot to train, right? So those things can be implemented also in medical, like rather than going like looking at a like plain 2D black and white image, you can take a 3D reconstructed like X-ray scan, and then the doctor can go through it, right? So there are a lot of different application, and it is when LLMs are taking over the world, this technology of like nerves or Gaussian splatting are also booming at the same time. Right. So now, how this like whole development came into the picture, right? All the problem of creating a 3D representation from the images has been there for ages, right? And one of the like unique solution was Bundler that came in early 2000s, right? And then came after the boom of deep learning era, right? Then the CNN based people thought, okay, we have CNN, why can't we use those CNN for getting a 3D model, right? So those CNN mesh based model also came in, and in 2020, we finally got the NeRF, right? So NeRF had multiple different phases of improvement through the Smith NeRF, Einstein NGP, those things. And finally, in 2023, we got to the 3D Gaussian splatting. So Gaussian splatting, what it is doing is that it is also doing the same like 3D reconstruction of the scenario. We'll go into that in more detail in the next webinar. But today we'll go into the NeRF and understand how NeRF works. Okay. So like when NeRF is there, so NeRF is neural radiant field, right? So neural is, there's a neural network involved in this somehow, and there's radiance fields. Radiant fields is nothing but representing a scene where you can move your camera. So based on the movement, you see different projection of light, right? Is a different way to represent a volume, right? So that NeRF can be also thought about as a scene parameterization. So generally, what neural network does is that it learns the parameter that represent your data set, right? Same thing is happening over here as well. And what NeRF is doing is that it's trying to understand the scene, right? And how it's doing is that it has a neural network with a volume rendering component added to it, right? So what volume rendering is nothing but is that it's not a surface rendering, right? We'll go in more detail on volume rendering later on. So let's move forward. So what now we understand from 1,000 feet overview, okay, what it does, right? But how it does, let's understand that with this step. So first step we have went through structure of motion, but we'll go through the data preparation step. In step 2, we'll do how the scene parameterization is being done, and then we'll understand what is the role of volume rendering. And on the third, which we'll discuss the improvement that the author showed in the paper for getting better results, right? So step 1.
Can we actually go back to the previous slide? I just want to, yes.
Yeah, this
So,
one.
yeah, I just want to summarize one more time what are the various steps that are happening. In the first step, right, we collect data, we actually take pictures of the same scene. You can imagine for simplicity, let's say you have a single object in the middle and you're going around the object and capturing many photos of the object, right? Now, the first step you need to do is find out what the camera location was, right? Because we don't know the camera location, we just have images. That is why you need step 1, which is structure from motion. We'll use Colmap to recover the camera position. Next, we need to represent this this volume, right, that we are going to render. This volume we need to represent in certain ways. And as Samyuda mentioned, that this representation is not going to be like a traditional surface rendering. This would be like a volume rendering. To understand volume rendering, just think about it, that we are going to represent the 3D scene as if it is, it consists of objects which are like fog, right? That light can pass through them, right? It doesn't reflect back, but light can pass through them, right? That is how this scene would be represented. So the entire scene, and then once you have this volume representation, right? The volume representation is basically, some representation of the volume where it is not surface representation, right? It is basically representing the color of the volume at every pixel or voxel, and also the density, right? Then we have the third component is volume rendering. Now you have this representation that you have learned, right? But you still, it's still useless unless you are able to render this volume, right? Make it into 2D images, right? From the 3D representation, you have to go to 2D representation, and that is what step 3 does. The naive version of step 3 doesn't produce excellent results, so we will have an improved version of step 3, which is hierarchical volume sampling and positional encoding. So those are the various steps. All right, let's go.
Yep. To the point. Yeah. So let's go to the step 1. So data preparation. So generally, there are a lot of caveats when you are collecting the data, right? So the main thing that you need to care about is that the lighting, that there should be a constant lighting. The lighting should not move, And second is that there should not be any moving dynamic objects, right? So that is two things that is there. And third thing is that there should be featured, there should not be any object that is featureless, like any blank paper or any like one color, no feature, nothing, right? So because if there is no feature, your structure for motion is not going to work, because it's not going to able to find the features that is going to match, and then it does the triangulation to get the points, right? So that thing need to be cared of. And apart from that, the environment should be like very controlled environment, right? So generally there are few steps thinking about this, right? So if there's a like tall object that you want to take a video and create a 3D representation, for that it is more better for you to do a arc plus pedestal. What pedestal is that you do a circle, and from there along the z-axis you translate, right? And then again do a arc, and then again do a translate, right? Rather than like taking arcs and tilting your camera to get the scene, which will give you a lot of images from those angles, but it will not be much like variation, right? Because you are not translating the camera, it is not moving, it is there, and you are taking the image, right? So as you know also that MLP neural network needs data, right? And if there is no variation in the data, your model will not be able to represent the scene properly. Same thing with these things.
One
If there is
other,
any,
can I add one more thing to it, just to add to
yeah,
what
yeah,
you just
sure.
said, previous slide. Yeah. So if you look at the first method, arc plus pedestal, there when the camera is moving, both the location XYZ of the camera as well as the direction is changing, right? So
Right,
the camera has 6 parameters, right? 6 degrees of freedom. It can
right,
translate in 3 directions, XYZ, and it can rotate in 3 directions, right? And when we are doing that arc plus pedestal, it is using both rotation and translation is changing. When we do arc plus tilt, so when you tilt, the camera doesn't move, right? You're tilting just the camera up and down or sideways. It doesn't, the XYZ position doesn't change. And therefore, even though you have given it an additional image, the image doesn't have the variation, right? It is not an ideal image because the XYZ location did not change. And ideally, when we are collecting data, the variation in the image is more important than the number of images, right? So the
yep.
variety is where the information is, right?
Yeah, that's true. That's true.
Okay.
To the point. Yeah. So, following with that, like same logic is also applied over here. Is that if there is any small object, the idea here is to try to get all the different angles and do a lot of translation and rotation to capture the 3D scene, right? Same here with the small bucket of fruits. You can see this like arc plus boom. Is that like you're doing arc and moving with a slight tilt, right, along the z-axis, and then there's truck plus pedestal. So it's nothing but that there's a lot of stuff in a rack. What you do is that you take a zigzag pattern of taking the images, right? And also same with the if there's a very big like your home or something. So what it does is that you should what you should do is that you take a translation, and along the corner you don't just rotate your camera and just start moving. You like move along the direction and then do a rotation with an arc, and then you move along with the other edge, right? So those things are need to be care of. And after that you have done with the data preparation and did your structure for motion using cold map. What you do is that you do the training, right? Now let's understand how the training pipeline looks like. So the training pipeline is very simple. So the first step that we have talked about is getting the 5D position. They generally it's 60 for the camera, but they are representing as a NDC, right? So which is like normalized device coordinate. So for those for that coordinate system, what it does is that there is a XYZ coordinate for the position, and that theta and phi is for the direction, right, of the camera. So you get a 5D input, you give it to this neural network f theta, and it gives you this 4D output, which is RJB plus this this opacity, right? So after you get this RGB opacity, or you can call it density, right? What you do is that you do volume rendering. So volume rendering is nothing but rendering your 3D volume into a 2D, right? And when you get this 2D image, you compare with the same image that was taken from that camera angle, and you compute the loss and any gradients that is being computed, and you backpropagate those gradient to update the model parameters, right? So over here, what is happening is that this image in the first step, from the image, from each pixel of the image, we are shooting out rays into the volume, right? And along those rays, we are sampling points, and we are giving the XYZ coordinate plus the direction of those points that are on the line, right? So this is a very this thing is done mostly in like volume rendering and those kind of computer graphics scenarios, which is similar to like ray tracing, how ray tracing works, but instead it is passing through the object rather than reflecting back from the surface, right? So same thing that what I've discussed previously also, it's a 5D input, 4D output, right? Now
Well,
let's understand.
can I go? I just want to add one more thing. If you
Yep,
go back to the
sure.
previous. So
Yeah.
here, actually, in the next slide.
This one?
Yeah. So basically, the neural network, right here, that f theta, right, that is the neural network, right? Forget about what's inside it. Consider it as a black box, right? And think about the neural network as a black box with certain knobs, right? And the input to the neural network in this specific case is a 5D coordinate, x, y, z, theta, and phi, right? So this is basically for any XYZ. So XYZ is basically spatial coordinate, right? So you're
Right.
saying that there is a point in space here, right? XYZ, right? And for now, forget about theta and phi, right? Let's say this point, right? And for now, also forget about sigma in the end, right? The opacity. If in this space, I could say that, okay, this is the spatial coordinate, and in this spatial coordinate, the color of the spatial coordinate is RGB, some color, let's say purple, right? So this point in space is purple in color. If I could find a neural network that encodes that spatial color, then I can, whenever I see that object, right? Whenever I see that XYZ, I could say, okay, render this color, right? And on the screen, I would render that color. The problem is that just specifying the color is not sufficient. Because the color depends on the viewing angle, right? So this point in space, you also can view it from different angles and it will change, especially for if you think about shiny objects, right? Let's say a red ball, right? You're looking at a red ball, which is shiny, right? And there is light falling on it, and you try to move your head. Depending on your viewing angle, the color of that thing will change, right? Because it can have a specular highlight on top of it. So the color will change. So obviously the color doesn't depend on just XYZ. The location doesn't determine the color. It also depends on the viewing angle. Okay. And that is why to encode the viewing angle, we have theta and phi. Finally, like I said, that this doesn't treat the whole scene as surface. It treats the whole scene as a volume, right? So that it can also handle fog and other things, right? Those kinds of things. So there also needs to be a density, right? So suppose in the scene you have something that some semi-transparent object, and through that you can see, right? So you could say that this transparent object has some density, right? It is not 1, it is less than 1, right? And then you get that is how they can model things that are see-through, right? So now imagine that this neural network is able to predict, right? Forget about how it does it. For any location and viewing direction, for any location XYZ you give it, and any viewing direction, it is able to output a color and an opacity, right? So if you can do that, then you can build, that's how the 3D scene is encoded, right? And as you can imagine, let's say this is how the 3D scene is encoded. If you want to render this 3D scene, you first specify the location of the camera. From the location of the camera, you shoot a ray, and it obviously goes through multiple 3D locations, right? It is a ray that is passing through multiple 3D location. For every 3D location, you know the XYZ, right? And because you're shooting a ray, you know the angle. And therefore, all the material it is going through, you will know the RGB color and the opacity. And you can keep adding the RGB color and the opacity and then blending them together into an image, right? Now, if this
Yep.
is not clear, just remember from this slide, only remember that this is how we are encoding the neural network, the scene first. The 3D volume that you are interested in, it is being encoded using the XYZ position and the viewing angle.
And
For
the
the
thing,
XYZ position and viewing angle, we are outputting an RGB color and a sigma, which is the density. So
right.
for now, we can remember this and move forward.
Yep, yep. This is how what is the input and what is the output, what the model is taking, right? Now let's understand how the like neural network that is mentioned in the paper is doing the job, right? For scene parameterization. So for that, what we are giving input is that we are giving this the gamma x, which is nothing but the XYZ coordinate of that camera position, and from there there are like 8 different linear plus ReLU layers, right? And in between there's a from first and the fifth there's a skip connection is there, and after the 8th layer there's a output from a linear layer, which is nothing but the density, right? That RGB and sigma, that's sigma, right? So, and after the 8th layer, there's the 9th layer where we are concatenating the position, that XYZ coordinate, with the direction theta and sigma, right? Theta and phi, right? And we are passing it to another linear plus ReLU layer, which is giving us this linear, then we're passing to another linear layer, which is giving us this RGB values, right? Which is very simple, very like minimal is there, and the skip condition is there to like prevent the overfitting, and that's how the MLP is structured, right? So now that we understand how the internal model neural network is done, let's understand how the volume rendering part is done also, right?
Can I also add a small commentary here?
Yeah, sure.
So for people who are new to neural networks, right? You can forget about the skip connection. Don't worry about it, right? It is something that improves the performance of the neural network because it solves a few problems like the vanishing gradient problem. Actually, don't worry about it, right? It is something that helps train the neural network better, right? So forget about it. Now you have as the input the gamma x that you see, think about it as just XYZ coordinates, right? So the XYZ coordinates are being transformed by the neural network. And then it is being used. Just imagine the neural network as a black box. It takes the XYZ coordinates and it outputs uh, the sigma, right? The density. On the other hand, because the density doesn't depend on the viewing angle, right? The how dense a pixel or a location is, you could say that it doesn't depend on the viewing angle, but the color depends on the viewing angle because of specular highlights. And that is why you can see that in this part, on the left part, you have additional, the D stands for direction, right? So that direction information is being fed into the neural network. So while predicting the RGB color, we are using both the direction and the location of this 3D volume. But when we are predicting the opacity, then the density, we are only using the location of this 3D point, right? And that's all this neural network does. It tries to predict these two values, right? RGB, not these four values, RGB and density. Given the inputs are in green, you can see that input is XYZ and the direction, right?
Right.
And then it's a very standard neural network. If you do not know about neural networks, you can think about it as a black box whose knobs need to be tuned.
Right. And another thing that I forgot to mention, that we are using this gamma function here, right? Which we'll talk about in detail, which is used for positional encoding, right? We'll talk about this later in the slides. All right.
Yeah.
So let's move on. So now comes the volume rendering part. So generally in early 19th, there was this problem of how do you like render, get a 3D render, get a render of a like volume, which is something like smoke or fog or cloud, those kind of things, which has a lot of particles, right? But and also at the see-through at the same time, right? Semi-transparent, right? So how do you do that? So generally, uh, the traditional approach is that doing surface rendering, which
So
is like
maybe,
you.
can I interrupt one more time? I'm sorry.
Yeah,
Can
I'm
we go
really
back
sorry.
a few steps? Yeah, one more step. Yeah. So we forgot to mention here how the neural network is trained, right? We went to step 3, but so this is the neural network architecture. To train it, you basically know, remember that from structure from motion, we know the camera location,
Right.
where the camera is located. So we can shoot rays through these pixels. And for every pixel, right, we will know that, okay, it goes and strikes these XY. So all the images that we took and the information from Colmap, which tells us how this image was, what was the viewing direction for these images, we can use all that information to train this neural network, right? And it is very standard back propagation algorithm that is used to train this neural network. And now we
Right.
can basically we have the input, direction, etc., and we have the output color from these images. And then any neural network training is basically an optimization problem that you solve using back propagation, right? Once you
Right.
have the input and the output, you can train a neural network to find the mapping. So that's one thing. The other thing is that usually when you train a neural network, you want to prevent something called overfitting, right? You don't want the network to overfit. When training a nerve, you want it to overfit, right? Because
Right.
you are encoding this scene and you don't want it to generalize. You don't want it for
Right.
every other scene. This neural network is only for one scene, right, that we are interested in. And so that's another little point.
Right.
It's
Right.
a useful interview question. If somebody asks you if
Yeah.
overfitting is ever useful, right? Most people would say, no,
Right.
it's never a good thing, right? But yes, there is one application where overfitting is the right thing.
Yeah. Or if you have a demo and you are very close to the deadline, or you are just on the scene, you are just fitting in and just showing the model that it runs. All right. So, yeah.
Okay.
So, like what Satya sir said is that that what we are getting is this tiny points, the RGB value, RGB and sigma value for this tiny points. But remember, guys, so this thing is not in 3D. It's still in 3D, right? But what we need is that we need 2D. And how do
Yeah.
you get to the 2D? We go to volume rendering,
Right.
right? We go volume rendering, and from volume rendering we do the L2,
No.
L2 with the ground truth, and we get the loss. We'll come to that more later, but let's understand how the from 3D to 2D is happening right now,
Right.
right? So talked about this. That is a very hard problem at one point, but later when like ray marching came along, right? Ray marching came along. What's the ray marching is doing is that, so generally, if you do ray tracing, you might have heard about ray tracing, path tracing. That anybody, people doing gaming and all, high graphics, you do path tracing, right? So, but there's also ray marching. So what ray marching does is that instead of just going to the object and reflecting back from the surface, what it does is that it goes through the object, right? And from there, wherever it is getting hit by the object, it records its color, right? It records its color, and we assign based on the distance or some more preference that if we should give more preference to which color, right? So over here you can see that this initial this initial 3 points, it is not hitting anything, so it's white. Now after that, it is hitting this first rock, so the weight assigned to this color is much more higher. And after that, there is this another rock part and another grass, right? So generally, what volume rendering does is a very sophisticated way of doing weighted sum, right? You know about weighted sum, right? There's a weight, and with some x value, you do a weighted sum, right? So what volume rendering is doing, and it is calculating the value for this w, right? So how the w is decided, that is done through that. Now let's understand like what is the mathematical part involved in this. I'll not go too deep, but the slides are here for you to reference, right? So what is happening, we have talked about this, that the camera is shooting rays to the volume, right? So the volume is consists of particles, and what we assume is that each particle has some density and some color associated with it. And what we want to know, if we are throwing any ray into the volume, where in which particle it is getting hit on, right? And what is the color associated, right? And from there we can do the 2D representation, right? So for that, we first need to know what is the equation of this line, how the line is represented, which is normal line equation. We know the O is nothing but the location, this XYZ coordinate of this camera, and then comes T. T is nothing but what is the distance from the camera. We can think of it as y is equal to mx plus c, right? So this is the x part. And then comes the d part, which is nothing but, oh sorry, so generally d part is the distance and t is the like ray direction. uh, I think I have missed this part. So
Well,
generally it
it's
is d is the ray direction and t is the x part, right?
yeah.
So at a fix over there, right? And apart from that, like now that we understand how the ray is going on and what associated with each particle, what we want to know generally is that like we are shooting a ray, what is the probability to hit at this point t, right? So for that, what we do is that we do sigma t dt. Sigma t is nothing but a unit volume along the ray, and we multiply it with dt. So if there is this ray and this is t, so what we need to know that it is hitting at dt, right? This is what we need to know. And from there, apart from this knowing hitting at t, what we also want to know is that probability of not hitting anything before reaching this t, right? Which is nothing but transmittance, right? So combining these two things, what we get is that hitting like first hit at t, right? Which is like we are without hitting any particle along the ray, we are hitting at t, right? Which is multiplication of probability for the p no hit before t, and which is probability of hit at t, right? And I'll not go too much into the detail of how these things are being calculated, how the transmittance is being calculated. But remember, this is the equation one, and we're going to come to this equation as well, right? So if you put the values for these probabilities, it is going to come like this, right? And afterward, after doing a little bit more simplification and applying more integration and Taylor's expansion, what we arrive at is this t, value of transmittance, which is nothing but negative exponential of this integration of the density along the ray, right? So after you get the transmittance, you put that value to the equation 1, right, that we talked about. So which gives us this probability of not hitting anything and reaching at t, right? So if you multiply that part with the color of a point t, right, you get the, and do a integration over from t0 to t1. What you get is the probability density of the color along the ray, right? But remember, this is a nested integration. So for what they did is that they discretize the whole thing, right? They discretize the whole this line, and get a proper quadrature uniform distributed points t1, t2, t3, which are like t1 ti plus 1 ti plus 1 minus ti is the delta, right? So this is how they do the how they discretize the whole thing. And from there, if you do a lot more like simplification of the whole equation, you arrive at this equation, which is like tc, which is the transmitter and color, and you get this 1 minus exponential of sigma and delta, which is nothing but alpha, which is the alpha composing that you do in normal Photoshop or something. This is the same exact equation of that. And we consider this t into 1 minus exponential as a weight, and we arrive at this final equation of color along the ray. Right now that we know this color along the ray, we can sample any point, and we know the color along the ray, and we create a 3D render. Right, this is how you do the how the 3D render is coming from volume rendering. So now that we understand, any points that you want to add?
Yeah, I want to add one point. I mean, because it's so mathematical, people may get confused. The main thing you have to take away from this volume rendering expression is that we are shooting a ray through this volume, right? Think about it as if you're going through smoke or something like that. Where the smoke is dense, it will not transmit as much. Where the smoke is not as dense, it will transmit more of that light, right? And then as the ray passes through it, we want to integrate, right? That summation sign comes because we are adding up all those colors, right? For example, there is smoke, and then behind that there is grass. We are adding up all those colors, right, as it passes through. Uh, in this naive rendering approach, we are sampling the ray equally, right? We don't know. So even if you look at this area between the camera and the cloud, there's nothing in between, right? There is nothing in between, but we are still doing all the calculation in this area before it hits the cloud kind of thing, right? Equally, right? We are giving as if they are of equal importance, and we are doing all the calculation necessary, right? Even in that free space, right? So that's the naive volumetric rendering, which doesn't, it takes a long time, and we'll see how we actually don't have to do that. There is a clever way of finding out this free space and then focusing all the energy into getting more, discretizing the volume, which is useful, right, for calculating the color more finely compared to the free space, right? So that's the main idea of the next idea we are going to talk about, which is
Right.
hierarchical volume rendering. Yeah.
Right. So, like over here, your pipeline is actually done. Like all the pipeline that we talked about in the step 2 of like, okay, we do SFM, we do a model will predict RGB alpha. From there, we'll do volume rendering. We compare those things, right? So now the volume rendering is done. Like you can get output from there, but the output is not good. Why? And not good, as well as it is not like computationally efficient. Why? Because we are like sampling in the phase space, what's the tool, right? So now we'll go on the improvement part of the rendering and positional encoding, right? So what hierarchical very mouthful, I think. So hierarchical volume sampling is doing is that you do the sampling of this white points, right? You do the sampling for this white points, and after this white points, you understand what is the weight associated with these points, right? And when you understand what is the weight associated for all of this point, if the weight for this value, this point will be much more greater than this point, right? W0, right? So from there you can understand is that this is a surface, right? So what we want to do is we sample more point along the surface rather than sampling in the free space, right? This is the what is the purpose of hierarchical sampling. And how they are doing it is that they have two neural network. If you go through the paper, there are two neural network, right? Coarse and fine. What course is doing is that we are giving it a uniform sample point that we have shown previously, the white points, and giving it XYZ location and direction. And after that, it is giving us the density and the RGB. From there, we are doing volume rendering. After volume rendering, we know we get the weights. And when we get the weights, we do PDF sampling. So over here, this is the based on probability distribution, we are sampling along the ray, right? So more points where the density is high, right? And based on that, we get the XYZ points which are more closer to the surface. And from there, we pass it to the fine neural network. We get the again RGB and density and RGB, and from there we get the final render. Right. This is how the hierarchical sampling is being done. Right. So uh, so after
Can
that,
you go? Yeah. So just to add to your point,
yeah,
if you go back to the previous slide. So in this
yeah,
slide, you can see that in the coarse sampling, the white points that we that have been represented, right? That is the coarse sampling. So we are first coarsely sampling the ray, and we are getting the white points. We are getting the weights at the white points, right? Now, based on that, we can say that, oh, the first, between the camera and the first point, there is no, there is no volume there, most likely, right? So don't sample there, right? On the other hand, if you go nearer to that object, you will see that oh, there are there are 2 points which show that there is density there. So sample more closely. So the orange dots there, they show fine sampling, the second neural network, and the first one is basically the white ones are based on the first one, right? That is how you can spend all the effort in getting better quality, spending all the computational effort in that area instead of the sparse areas.
right, right. Yeah. So this is how the hierarchical sampling is done, and after that comes the positional encoding, right? So so in this part, what happens is that generally for neural network, it is better to give it much more like high dimensional data rather than low dimensional data, right? Because it is not able to understand the representation, the parameters. It needs to figure out the data distribution, right? So over
Actually,
here,
can we go back to the previous slide? I'll explain a little
yeah,
bit. Now,
yeah, yeah,
the neural network, the input to this neural network is the five dimensions, right? X, Y, Z, and theta and phi. So three location and two for directions, right? But in reality, I mean, we did not mention it yet. We are going to mention it now. In reality, we actually do not use XYZ. We don't use these five-dimensional space. We convert these 5 dimensions to a much higher dimension, right? In fact, each X would be converted to, let's say, I think 10 or so numbers. The Y would be converted to 10 or so numbers, and so on and so forth. So you may be thinking that why do we convert this 5-dimensional space to a 60-dimensional space? Uh, the information should be there in this 5-dimensional space, right? To give that intuition, we have included this slide where this is from a standard classification problem, right? You have two kinds of dots here, the blue dot and the red dot, right? And we know, I mean, the dot actually doesn't have any color. They are just shown to represent a class, right? So blue is a different class than red. The only information here is positional data, which is X and Y. So for a human eye, it's very simple. You can see that, oh, there is a ring inside, there is a ring outside. I'll call all the rings inside blue points. I'll take all the rings outside as red points. So it's very simple for humans to do it. But when you talk about neural networks or any
Parameterization methods.
yeah, any kind of support vector machine or something like that, they don't do very well when you have this nonlinearity. They want to cut things into using lines or planes, right? So if things are on one side of the line or the other side of the line or one side of the plane or other side of the plane, they have a much easier time, these neural networks or any machine learning technique, right? Because this shape, visually we can see this shape is easy to do, but it's not very easy for neural networks. So, but let's say you take the X and Y coordinates and make a Z coordinate. Z coordinate is nothing but X squared plus Y squared, right? So now you can see that the red points, if you add this Z coordinates, instead of just doing machine learning on X and Y, you do machine learning on X, Y, Z, where Z is nothing but X squared plus Y squared. You can see that Z will separate out, right? In the Z direction, these two things will separate out and you can easily cut out through a plane, right? So the information becomes very easy for the neural network or support vector machine for anything to consume. So we are assisting by manipulating this X and Y, taking it to a higher dimension, right? And that is why when we take X, Y, Z, phi, and theta into a higher dimension, it becomes easier for the NeRF to consume that data and to manipulate that data to easily use that data. Now we are hitting the 10, 1 hour mark. Should we do our quick giveaway question and then we will continue with this?
Yeah, I think that's a great idea. Do me a favor and go ahead and unshare your screen for a moment there while we do our trivia.
Yep.
Awesome, thank you. So far, I mean, this is quite an in-depth look at NeRFs. I gotta admit, I didn't really know how they worked, and I'm getting closer every minute here. So, yes, folks. So the way this works, if you need a reminder or you're joining us for the first time, is I'm going to ask one trivia question based on the presentation so far. And the first person to answer that question correctly in the Zoom chat window with the messages being sent to everyone, not just hosts and panelists, that's important here, will win the OpenCV University course of their choosing. If you're not in the Zoom chat, you can get there by going to opencv.live in your web browser and we'll pop open Zoom for you. I'll give you a second or two to do that. Also, if you have won in the last couple of months, do not answer, please, and give someone else a chance to win. We've got a few trivia sharks out there. We had to add a disclaimer. So today we've been talking a whole bunch about NeRFs. This one is going to be a two-parter. You have to answer both parts of the question in one message in the chat out there, folks. So, in what year was this NeRF paper first published, and at what conference? What conference was this? Oh, wow, man, just friggin' nailed it there. Damien LaRoque. Damien LaRoque. The answer was ECCV, European Conference on Computer Vision, in 2020. That was what we were looking for. Right on, Damien. You got super quick on that one. Go check out OpenCV University. It's opencv.org/university. You can see what courses are there on OpenCVU and choose one. And then when you have a course that it looks like you want to take it, send one email to me, that's phil@opencv.org, with the name of your course, and we'll make sure that it shows up in your dashboard. Yeah, congrats on the winner there. I don't know how you got that one so quick.
Very fast. I was thinking that your question would be, because I don't know these questions beforehand, right? So I was thinking that your question will be about Colmap. But people they're also thinking that, so
Yeah, I tried to swerve them, and instead they swerved me. It happens. It happens. All right, let's continue there.
Yeah.
Damien had the archive paper right next to him.
Smart. See, I posted. We reward people for paying attention. I posted the archive paper link earlier in the Zoom chat, and so people that were paying attention, they had a leg up.
Yep, didn't take time. Okay. Uh, so carrying out with the discussion that was going on positional encoding. So you can see the difference between how what is the render that we're getting with and without the positional encoding, right? And like how it is happening is that I will give a brief story over here. So generally what the author tried is that, okay, we have an image given the xyz coordinate. If the model is able to get the predict the color RGB value associated with that pixel coordinate, right? So the authors tried to model the problem and train the neural network for a long amount of time. So whatever they did, they came up with this blue box, very pixelated version of lion taking its tongue out, right? So, but it's not there. It's not how the actually it should look like. But then they understood that the deep neural networks are biased toward learning low frequency functions, right? So the low frequency function that is there, which is can be learned very easily, they are just learning that and missing out on the more finer detail that is present in the image. So for that, what they thought of is that, okay, what we'll do is that, okay, we only have x and y, right, which is very small dimensional data that we're giving. Why not we just transform that data and get a multiple, maybe n dimension data that is representing the same x and y values, right? So that same idea they implemented and found out that there is a much more like clever way to represent low dimensional data, and it gets you the result that you want, right? So what happens is that you have this let me get my pen. Yeah, so you have this p variable. What you do is that you take a sine and cosine for a periodic function for sine and cosine, and you take it for like L amount of time, right, for the same variable. So if there is x, y, and z is there, so you will be doing sine of x with 2 to the power 0 to 5, and then again cos, right? So there'll be 2 into L amount of repetition of the same variable. So what we will get over here is that 2 into 10, as the authors are using 10 for representing the xyz coordinates. Like for all the xyz coordinates, they are using L equal to 10. And for direction is also the same. It's just that they are changing L from 10 to they are using 4, right? And this is how simply they parameterized, not parameterized, they transform the low dimensional data to a high dimensional data. So from there, they are getting a good representation of the 2D, right? Now, at the very end, what we do loss calculation, right? And the loss calculation doesn't leave out the coarse or only the fine tune. It takes both. We do L2 on both the coarse and fine output, and we get the total loss, and then we do backpropagation to update the variables. So this is how the entire NeRF pipeline looks like. The paper doesn't have this much detail, but we are like explaining a lot of detail, a lot of mathematics over here. So don't get bogged down. And this is how the entire pipeline looks like, right? Anything you want to add, sir?
In the previous slide.
Yeah.
So, some people may be thinking that, oh, how do you come up with these things, right? Is it obvious? The answer is it's not actually obvious, right? So
Yeah.
when I was a grad student, I used to read these papers and I used to think that, oh, these guys are so smart. They somehow figured it out. I'm a connection. How could you go? Why not use XYZ theta phi, right? Directly. That is what you would do normally, right? Why go to this higher dimensional space? How did they figure it out, right? The thing is that initially they did not, right? It's not obvious that you need to do this positional encoding, right? You
Right.
do it because you did not get good results with XYZ theta phi. And that's true with, there's a lot of trial and error that goes through. And we do not know what other things that they tried, which did not work, right? So they must have
Right.
tried other things also, which did not work. this particular positional encoding worked. Okay, there is some reason to it. There is, it's like a Fourier transform. It's using sines and cosines. It also has this other interesting property that things are not blowing up, right? Sine and cosine, they'll always produce numbers between -1 and 1. So things are not blowing up, they are constrained, right? So all those things are nice properties, but why this exact formation of positional encoding was used? Why not some other encoding? That is, I would say, trial and error, right? They must have tried other things, and this thing must have worked for them. But in the paper, right, people don't write, oh, I tried these 10 things that did not work. This is the one that worked, right? So for people who are saying there's nothing obvious about going from XYZ theta phi to this positional encoding. It is through trial and error, right? I'm saying this because as a grad student, I used to be very confused, right? Why am I not getting this connection? It is through trial and error that they got this.
Yeah, like we also had a very big discussion around this thing. I was thinking like, why can't they just add some noise at the time of calculating the loss and try to get it converged somehow? Like, but later on, like this is what they came up with, I think, and so that is the like generally it is not being told anywhere. You try maybe try 99% of time that one solution that comes up that does the job, right? So yeah, a lot of effort goes into this. So now that we understand like how the nerve works, let's understand how you can use nerve to create a 3D representation of a scene, right? So what you can do is that you can take this official implementation, which is TensorFlow, if you are using TensorFlow, or if not, you can directly go to Nerve Studio, which is a very good platform. It gives you a good visualizer, very few commands, you just run it and it like works, right? And if you are nerdy and want to just get into like how this thing is working, a simple implementation of Nerve in PyTorch, you can go through this GitHub. It will be shared. And also we have a very detailed article going through each and every code from this repository and explaining how Nerve works in Learn OpenCV, which later on can be shared as well, right?
Yeah.
And
Can you share that link right
yeah,
now to the Learn OpenCV link?
yeah, sure.
Yeah. But let me also tell you that nobody uses nerves anymore. So that is our invitation. It's very useful to learn, where how we reached the current state of the art. But it is also true that nerves are not used. Most of the time, they're not used anymore. It's replaced by something called Gaussian splats, which gives amazing results. It also is much faster. The quality as well as the speed is better than NERSC, and that we will cover in the next in our next webinar, right? Not
Yep.
next week, but a few weeks from now.
Right.
But
Okay.
it's very useful to learn some of these things, right? Because
Yeah.
you understand the basics of things. You also understand how to use it better, right? When you know the technical nitty-gritty, you know how to fix bugs, right? I'll give you one example. Can you show that that slide we pushed to the end for data capture, where we do
Uh,
for the trunk
which one?
and the
Oh,
next
right,
routine?
right, right. Yeah, let me. This one.
Yeah, but there was another one where we were going to the edge of a corner of
Right,
a
right, right. Yeah, yeah.
Yeah, so here, these are, we removed this slide because it was just too much. But let's say you're capturing a nerve, right? Uh, and you're in a corner of a room, right? The normal way to think about it, okay, you would actually do it the truck plus pan method, right? You would go and then turn around. There's a problem with that method, right? Because we are not getting enough data at the edge. At the edge, you can see that the camera rotates. It doesn't translate. So at the edge of this thing, right, where it is at the corner, you're simply rotating the camera, which is not a good movement for nerves, right? So the way to go about it is that you go, horizontally, you go vertically, and in the space you go outward. You go in an arc so that you're moving the camera as well as rotating the camera, right? In the other one, right, where it says truck and pan, you're simply rotating the camera, which doesn't have the same amount of information as movement plus rotation, right? So these kinds of things, right, you learn by, which is very, very practical information. You learn when the intrinsics of the system.
Right. Right. Very true.
So yeah, any other questions? We can take questions for another few minutes.
Yeah, we've got quite a few here. I think you mostly did a good job of answering them during the event here, but let me take a look at what we've got on the Q&A section here. So
Should I unshare the
Steve,
screen?
yeah, go
Yeah.
ahead. Steve
Yeah.
had a really good one up here. I'm not sure if we got to this one. If you scroll up in the chat a bit, you can see. He asks, how robust is the MLP for NeRF scene reconstruction to slight changes in colors, even when you're altering your XYZ camera position without changing the theta of the camera? Does that make sense?
Without altering the
Yeah, if you scroll up a little bit, 9:46 a.m. in the chat, you can, if you want to reread that one, you'll see what I mean.
Okay, with regards to angle affecting color, how much does the color change in angle? The calculation results with regards to the surface. Say the matte red ball that does not have specular highlight, but may have
Right.
colors that may vary from the true red to brick or a more orange color. Okay, yeah, so if there is, so because the way the radiance field is encoded, right, it actually doesn't, if you don't capture, let's say you have a ball, right, which looks very different, right, from as you change from one angle to another, yes, there will be there will be an effect if you have to sample that phenomenon very carefully, right? But if it is a continuous shift, right, and you can say that, okay, let's say in the extreme case, a part of the red ball becomes blue as you move it from the side, then obviously, you may not be able to know the transition. There are many ways to go from red to blue, right? And if you just have two samples, it will pick some transition, right? So yeah, so the more variation, the more complex the scene is, the more complex the objects in the scene are, the more complex their reflectances, the more images you will need, right? The denser sampling you will need.
Yeah, I think like this is what's called like view dependence, right? From different view, you should get different rendering of the scene, like the maybe water surface or something like that. But I don't, as Sir says, I don't think there's a much emphasis on view dependence on nerve, but Gaussian splatting does have that, and we can talk about that on the next
In the
webinar.
next yeah.
Yeah, right on. And so the part two of this look at sort of scene representation, modern scene representation, I guess we could call it, is currently scheduled for, I think, what do we have here? February. It looks like March 6th is what the next one is scheduled for. So we're about a little over a month from now. Coming up next
Well,
week
in the
on
meantime,
OpenCV Live, we've got Sebastian Prentice. You want to tell folks a little bit about next week's guest, Satya? Sebastian Prentice from Voulez-Vous.
Oh, so next week's guest, it's a fascinating, So he's a student from our course, and he took our course because he wanted to build an application. And this application is mostly built around generative AI, one of our courses. And it's an app which you take a picture of your, let's say you have vodka at home or some other, alcohol at home. You take a picture of it, and it will give you all the recipes, right, which are which you can make using alcohol.
Pretty cool.
Right?
Yeah.
Now you would be thinking, okay, so where is what vision technologies are used? First of all, you need to know what this bottle is, right?
Mm-hmm.
The second thing is that
There's a lot of different kinds of alcohol and a lot of different
there are
brands
like
of alcohol and
thousands
yeah.
of cocktails, right? So
Yeah.
there are thousands of cocktails that you can make. But if you take a picture, if you have a photographer actually make the cocktail, take a picture of it, that's going to cost you a ton of money, right? And
Yeah.
this is a startup. They were like a 2-person team initially, and they did not want to spend that much money. But one of them is a mixologist, right? So they actually
Okay.
rendered using generative AI, the techniques that they learned in our generative AI course. They rendered all these things, all these cocktails, and then the mixologist actually went through all the images to make sure that the rendering is correct, right? So like for every cocktail, they must have generated 10 or so, and then they picked the one that worked. If it did not work, they would change the prompt and create a new image, right?
Yeah.
But then you have these large number of images that also need to be centered. So they used a lot of vision algorithms to make sure that these images are all centered properly, because the generated image didn't always produce centered images and things like that, right? So a lot
Sure.
of little things that went into this app. I'm really glad how students from our course, they are using what they learn in many different ways. I always
Yeah.
said that generative AI is a fun course. It's not a foundational course, and yet people are creating full-blown apps and companies from what they learned.
Yeah, definitely.
Nice idea, to be honest.
Yeah.
Yeah, I look forward to that one. Next week, folks, same bat time, same bat channel. I think, Satya, you want to send us home?
Yeah, thank you so much for attending this webinar. We went over, and if you like these kinds of tutorials, please send us emails, give us feedback in any way possible, because we are always looking for the best way to serve our audience, and we feel that some of these tutorials are popular. But if you give us feedback, we will do more of these. And thank you, Soumyadeep, for creating these beautiful slides explaining the whole pipeline really well.
Pleasure is mine. Thank you so much.
Thank you. And we'll see you in the next webinar in March. We had to move it slightly, but it's in March.
Right.
And thank you, as always, Phil, for organizing the show. Nothing went wrong.
So far, yeah. Thank you to
Don't
our
lose the
audience.
recording.
Yes, thank you to our audience as always. Take care of yourselves out there, folks. Take care of somebody else if you can, and have a great day wherever you may be.
All right. Thank you.
Thank you.